All right, so thank you all for joining us this afternoon or morning, depending on where you might happen to be. I'm very excited to introduce my student, Aravind. He's been with me for a fair amount of time now, but he started at IIT Madras in 2012, where he got a Bachelor's and Master of Technology in the Aerospace department there. And he did a nice piece of work on vortex analysis with my PhD colleague, Kannan. And so when we were at Ocean Sciences early in 2018, Kannan told me he had a star student that would do a phenomenal piece of work for me, and he was absolutely correct. So Aravind joined us at Northeastern in the fall of 2018 and has been with me since. Just a short list of the accomplishments that he has achieved since being here. He's won numerous conference support scholarships. I think the chief accomplishment that I would say he achieved was the Cipolla Award, which is one of the top mechanical engineering graduate students in the department. He won that in 2020. I think perhaps the accomplishment he might value the most might be the Engineering as Art Award that he won for a beautiful turbulence visual that he produced, and that was in 2019. So yeah, like I said, more than impressed with Arvind's work over the past 5 years, and looking forward to seeing the presentation we did.
Thank you, Michael. That was a really kind introduction. And good afternoon, everyone, and good morning or good evening to those who are on Zoom. Thanks a lot for joining for my defense, whether you're here in person or on Zoom. As Michael mentioned, I just wanted to talk a little about some of the work that I've done over the last 5 years as a PhD student here at Northeastern with Michael. And most of my talk today is going to be revolving around Lagrangian convergence signatures on the surface of the ocean and how to measure it and how this links to material transport in the ocean, not just in the horizontal direction, but also in the out-of-plane vertical direction. So what you might notice in the background is, the image on the background was a satellite image taken by the Copernicus Sentinel to a satellite of a phytoplankton bloom in the Baltic Sea. And these green chlorophyll signatures indicate that there's a large concentration of phytoplankton along these very sharp filaments that wrap around into a vertical pattern. If you look closely, you can also see a ship and its wake here. And that essentially tells us about the length scales in the flow. And I am particularly interested in the width of this filament, which is approximately of the tens of meters, whereas the entire structure, the length scale associated with the eddying structure itself is around 3 kilometers. Now, such patterns, these large filament-like patterns, which accumulate material on the surface of the ocean, are found elsewhere as well. One example is that of the sargassum, which is essentially brown seaweed that has accumulated along a density front, which is a region where dense water from the sea meets lighter water near the coast. So this photo was taken near Florida. Another example is from the oil spill as a result of the Deepwater Horizon event in the Gulf of Mexico. And even plastic waste on the ocean can sometimes organize itself along these sharp filament-like structures near density fronts of the ocean. What all of these have in common is the length scale associated with this filament, or they have very high aspect ratios and are kilometers long while only being tens of meters wide. Now, while all of these make some pretty pictures for us to look at, we really need to keep in mind that these can have really bad impacts on the environment. For example, it can be really hard to have such a high concentration of pollutants as well as the algal growth over a very short region in space. And although this might suggest that if we want to tackle pollution, for example, we can just go target these features in the ocean, we also need to keep in mind that if you're able to preempt where these patterns might emerge, it'll help us be better prepared to tackle events like the oil spill, for instance. Now, another phenomenon that is sometimes observed at these density fronts, where dense water meets lighter water, is that sometimes in localized regions, the dense water can get pulled underneath the lighter water. And when this happens, it also pulls with it the fluid and material from near the surface below to the ocean interior. Now, this process is called subduction, and it has been the primary objective of the project named Calypso, which basically funded most of my PhD research, was to investigate subduction in the ocean. So subduction plays a critical role in the exchange of fresh water, heat, nutrients, etc., from the surface of the ocean to the interior. And this example shown here shows how microorganisms named copepods that live in the sunlit layers near the ocean surface can get pulled underneath during subduction. And because they are capable of locomotion, they can swim back up. And as a result, at these fronts, when there's subduction, you see an increased concentration of these organisms not at the front, but towards the lighter side. And that is those are the regions which end up being feeding grounds for whales and other organisms, larger organisms. Now, subduction is obviously important, but it occurs only in localized regions along density fronts, for example. So one of the key questions that I wanted to address as part of my PhD was, how do I figure out where subduction can occur? This is one of the central themes I'll be discussing today, as you'll soon see later. The other concept that I've been talking about a lot is the concept of surface convergence or 2D convergence in the ocean. What is it and how do we measure it? Well, the traditional approach to quantify convergence in any fluid flow is to look at it from an Eulerian sense, which essentially asks us the question, what happens within a small region of interest at any instant in time? The other approach is the Lagrangian view, which essentially tries to look at what happens to an infinitesimal fluid patch as it evolves over a finite period of time. So, how do we quantify convergence? Well, from an Eulerian sense, the horizontal divergence essentially quantifies the mass inflow into the region, whereas the Lagrangian metric dilation rate, which was only recently introduced, quantifies how much the area of the fluid band changes over as time changes. All right, now if you look at these metrics, you might think, wait, these two look fairly similar. Is there a link between the two? And my answer would be yes. In fact, if you take the Eulerian divergence and you average it along a particle trajectory, it's not just a spatial average or a temporal average, it's a Lagrangian average along a particle trajectory, then you get the Lagrangian metric dilation. And in 2015, Huntley and the others showed that the dilation rate is what indeed captures these regions of strong convergence and material accumulation at the surface of the ocean. So what they did was they considered a regional ocean model, deployed plastic-like buoyant materials or particles on the surface of the ocean in a uniform 1 kilometer grid, and they had vectored the particles over 10 days and noticed that most of the particles aligned along these sharp filaments that you see in this image. They also computed divergence and dilation rate fields on the surface of the ocean. And the key observation here is that these black regions of high concentration of buoyant material correspond very well with regions of negative dilation rate indicated in blue on the right. Now, one thing we need to keep in mind is that the dilation rate metric is defined for an infinitesimal fluid patch, which can be computed in a numerical model. But how do we measure it in the ocean? That's another question I'll be talking about in detail today. Another thing you might have noticed is that the distribution of material on the image on the left was somewhat reminiscent of the phytoplankton distribution you saw earlier. But the moment we take a look at the scales associated with the two problems, well, the filaments approximately have similar length scales in terms of the width of the filament, but the sizes of the eddies are very different, by about orders of magnitude. In fact, the eddy you see on the left falls in the regime of the mesoscale flows in the ocean, which are fairly two-dimensional flows in some senses, which are non-divergent and have very low vertical velocity, very small vertical velocities compared to the horizontal velocities. And as a result, these convergent regions which accumulate material on the surface of the ocean cannot directly be linked to mesoscale flows. At the other extreme is the turbulent microscale, which is primarily involved with mixing and energy dissipation in the ocean. And these scales can also be relatively easily investigated using idealized numerical models or by just deploying instruments off the side of a boat to make measurements at these length scales. In between the two is the tricky submesoscales, which are weakly three-dimensional flows where the vertical velocities are larger than what you would see in mesoscales, and they are not non-divergent. And the filament-like features that you observed earlier are a result of submesoscale processes in the ocean, like density fronts or filaments that are spun out of the edges of mesoscale eddies usually. Now, even though there is a lot of practical importance to submesoscale features, it has been really difficult to observationally investigate these regimes because of the length and time scale associated with these flows. And as a result, we are not able to observationally study these features until probably the last decade or two. Even now, when we try to study the submesoscales, the observational data is fairly sparse. And so that is another question I try to address today. What happens if the available data is sparse? What can we do? So now that we have some idea about the background and some of the motivations for what I've been trying to do for the last 5 years, I'll just quickly give you an outline of what I'll be talking about today. First, I try to look for surface signatures of the subduction by trying to find a metric that can essentially identify regions of large vertical displacements of fluid over a finite time interval. Spoiler alert, it turns out to be the metric dilation rate. So the next project essentially discusses how to measure this dilation rate in the ocean. And finally, I talk about what can we do to estimate these dilation rates when the available data is sparse. All right, so moving on to the first project where I looked for surface signatures of subduction. Well, this was done thanks to my collaborators at UCSD, UI, and MIT, Dr. Verma and Professor Sarkar from UCSD, Dr. Fralick and Dr. Mahadevan from UI, and Dr. Haley and Dr. Lemuzio from MIT, who gave me really nice numerical simulations, which essentially helped me do whatever I wanted with the model. So because I had a numerical simulation, I had all three components of velocity and high resolution wherever I wanted, and I could freely compute three-dimensional trajectories of particles. But this is not the case in the ocean, because in the ocean, vertical velocities are usually small, and so it's really difficult to measure them. And even when you measure them, it's going to be really hard to obtain high-resolution 3D cubes of data, which is going to allow you to track what happens in a Lagrangian sense. But what is available, though, are surface data, either in the form of satellite maps or some other sources, which essentially can help you locate where these density fronts lie, for example, and then you can probably go look for subduction signatures near the fronts. And if you're near the coast, you can also get high resolution surface velocities using high frequency radar systems. So motivated by these, I decided it would be best for me to look for signatures of subduction on the ocean surface, which is where observational data is most widely available. So, as I was talking about earlier, I had access to 3 different numerical models. One was a turbulence resolving model of a density front. The other was a larger scale process study model for fronts in the ocean. And the final model I considered was the data simulated operational model of the Western Mediterranean Sea. And I obtained fairly qualitatively similar results. And so, for the sake of brevity, today I'll be talking about results from the last model, the operational model. Quick overview about the model. The simulations are done over a 430 by 270 kilometer square domain in the horizontal and has a 500 meter spatial resolution. And it has the capability to assimilate data almost in real time from satellites or even observational data. The image you see on the right is an instantaneous vorticity field in the region which kind of gives you an idea of the dominant flow features in the region. For example, you see this Western Alboran gyre and another nearby gyre, which are essentially expected to be regions around which you can expect density fronts, because this is where the dense salty Mediterranean water meets the fresher Atlantic water that comes in through the Strait of Gibraltar and then meanders around. Okay, so now I have access to the model. The first order of business for me is to quantify vertical displacement in some way. So what I did was I initialized particles throughout the entire computational domain near the surface, and I advected them using the full 3D velocity field for a period of 12 hours. And then I computed the vertical displacement of the particle over 12 hours, and the results are plotted here. And how to interpret this data is that any particle that started in the darkest black regions in the domain were vertically displaced by more than 40 meters over the course of 12 hours. And you see some familiar features, I guess, here. For example, if you look at the edge of the Western Alboran gyre, you see high vertical displacement. That is probably as a result of some mesoscale dynamics near density fronts. The next step for me was to decide on what metrics to look for at the surface so that I can potentially identify this large vertical displacement. The first metric, of course, since I have access to the model data, is the vertical velocity. So if I look at the negative vertical velocity, it indicates downward motions at that instant. The second metric was the density gradient magnitude, because this can tell me where the fronts lie, because we expect subduction to occur near density fronts.
I'm sorry.
Yes.
So you're saying metric, but I mean, delta Z itself is the thing you're trying to predict from this other stuff, right?
Yes.
And so when you say velocity, you mean just the instantaneous velocity at the initialization point?
Instantaneous velocity at the initialization point at the surface.
Okay.
Thank you. Do any of you have any other questions that I can clarify?
So the vertical velocity is obtained by, so that you have the surface velocity, right, from the,
Yes.
how do you obtain the vertical velocity?
I have the vertical velocity information from the model itself.
Okay.
So I just use that. For the third metric, I use the idea that convergence at the ocean surface has to correspond to downwelling because of conservation of mass. Now, this is applicable at an instant, and so I consider the Eulerian horizontal divergence on the surface as a third metric. And the next one is the Lagrangian version of divergence, the dilation rate. The last metric I consider is a metric that's related to dilation rate, FDLE, which does not measure convergence per se, but it is a measure of attraction of fluid particles towards a feature. So the way that I define these metrics, I should be able to look for the strongest regions in these fields, and ideally they should correspond to strong vertical displacement. For brevity, I'll be talking about only the divergence and dilation rate today. And if we look at the divergence field and the dilation rate field, these fields share some similarities with the delta Z fields. For example, the edge of the Western Alboran gyre, where you see large displacements, are somewhat captured by both. But the idea is that the strongest regions need to correspond to this, from the surface metrics, need to correspond to strong vertical displacement, because the whole idea behind this is to narrow down the search for where subduction could occur. So I choose the top 1% regions in both of these fields as our target zones where we expect large vertical displacements, and then overlay them on the delta Z field. What we observe is that the dilation rate target zones do a much better job of capturing where large delta Z is observed. If I try to quantify this overlap by using some skill metrics, the first metric I considered is the complementary CDF, which essentially tells me what is the probability of identifying a vertical displacement of at least delta x. So if I take the dilation rate curve, the blue curve in this plot, and I look at where delta Z corresponding to 20 is, what this data point tells me is that if I look at the dilation rate target zones on the surface, we can expect vertical displacements of 20 meters or more 30% of the time. The key observation here is that the two Lagrangian metrics perform much better than any other Eulerian metric, which of course do better than randomly sampling the domain, of course. And this is not the only metric that I was interested in. I was also interested in what fraction of the strongest displacing regions are captured by our target zones. So that is quantified by my target efficiency. And here I see a much more striking result, which is that the strongest regions of displacement in the domain are being identified by these the target zones of these Lagrangian metrics.
So I'm a
Yes.
little bit confused, why you're parameterizing this whole, this whole quantification of how good the metric is, using delta Z as a parameter. Do you have like a physical notion of what, for a 12-hour window, what the characteristic delta Z should be for a typical downwelling that you're interested in?
That's
Why
a
don't you
great
just- why
point
don't
you
you just
raised.
look at that delta Z. Okay.
So subduction is said to occur when fluid and material leave what is known as the mixed layer in the ocean, which is where you see a lot of mixing happening. And the idea is that once you leave the mixed layer, whatever has gone below the mixed layer would probably stay there for a long time. In this model, this data, of course, is consistent with what is observed.
What is a long time?
It depends on the problem, but the temporal scales associated with submesoscale flows would be of the order of a day or more. Now, for this model, at least for the instant that I was considering, the mixed layer depths on an average correspond to about 15 to 20 meters. So I would assume that if I see displacements more than 15 meters, it could correspond to subduction, but then I will have to do a one-to-one mapping to be absolutely sure. Do you have any other questions? Okay, so this study kind of establishes dilation rate as a good metric to locate where large vertical displacements would occur in the ocean. The problem is we can compute this in a model, but how do we measure this in the ocean itself? That is a problem that I try to address in my next project, which was done in collaboration with Dr. Huntley from Rowan University and Dr. Kerwin from Delaware. So the idea here was that when I look for surface fields that I can obtain, for example, from satellite altimetry, which essentially measures the sea surface height, there is a method to obtain divergence-free velocities. But the problem is when velocity fields are divergence-free, the Lagrangian dilation rate metric will be uniformly zero everywhere. So these velocity fields cannot give me any dilation rates. The other option to get velocity fields on the ocean surface is to use high-frequency radar systems, but these are applicable only near the coast. And if I'm out in the open ocean, this is not going to be of much help. But what is available during field experiments are Lagrangian instruments called drifters, which are essentially instruments with a buoyant head that allow it to float on the surface of the ocean. And they also have this stroke, which allow it to track the currents at a design depth. The image here essentially shows you the trajectories of a cluster of 27 drifters that were released in a fairly tight cluster in the Western Mediterranean. And over the course of about 25 to 30 days, they do a pretty good job of mapping out the various flow features in the region. So the idea we had was to potentially use these drifters to somehow estimate dilation rates. Now, one thing we need to keep in mind is that we get the drifter locations using GPS units that are inbuilt. And experiments have shown that these GPS units have an uncertainty of about 6 meters when you try to extract the positions. So the idea is that, okay, we need to estimate dilation rates and we need to use these imprecise instruments in a sense. What is the best strategy to do this? So essentially, before I talk about the method, let us take a step back and try to understand how dilation rate is measured. So as I've been mentioning, the core assumption behind this whole method is to consider an infinitesimally small fluid patch. So the assumption is that if I'm considering the evolution of a fluid patch over a finite interval of time, we can always consider a fluid patch that is small enough such that it will deform in a linear fashion from a circle to an ellipse. Once we obtain this mapping, we can define the dilation rate as the logarithm of the product of mu1 and mu2 corresponding to the major and minor axes over the time interval. And this can be rewritten in an area-based definition as the log of the area ratio or time. Now, this area-based definition helps us when we're dealing with finite size fluid patches, because now the finite size fluid patches are no longer going to deform into an ellipse or a finite interval of time. But even then, if we need to track the finite size patches accurately using drifters, we'll have to use an infinite number of drifters to accurately capture how this boundary deforms. That is not possible because during field experiments, we are only going to have a finite number of drifters at our disposal. So we're obviously going to have to discretize the boundary, and this is going to introduce some error into our estimates. The other source of error comes from the accuracy of the GPS units. And so whenever I make these drifter-based dilation rate estimates, I'll have to account for a combined effect of these factors. So first, let us consider the effect of boundary discretization. Now here, I have focused on a pretty active region of the flow inside the Western Mediterranean Sea, and I have plotted dilation rates measured at each point using a finite size circular fluid patch with a length scale of about 100 meters on the top. And on the bottom, I have a similar field, but this time I've computed the dilation rates using drifter triads. Essentially, I have drifters at the vertices of an equilateral triangle when I deploy them. What I observe here is that overall, the fields look very similar, but the field at the bottom looks a bit noisy, especially when I'm looking in these strongly converging regions. So to understand this a little better, I can look at a vertical transect and look at how the two dilation rates compare. And we see that there's a pretty good agreement between the two, except when we hit this strong convergence region, where we see some error. But then I just decided to focus on the absolute worst case scenario here. Over here, where there exists a strong filament of divergence right next to a strong filament of convergence. And if I look at the transect, I see that the drifter-based estimate somehow completely misses this convergent extremum. If we think about why that's happening, it's most probably because if you track the fluid patch accurately, because of filamentation, it can stretch out and still lose area. But the moment we start discretizing it, because of effects like these, we might end up considering larger triangles than what we started with. Now, this can give us positive dilation rates. To avoid this, I can try to increase the number of drifters per estimate. And if I consider a triad, okay, the error has gone down a little, but I'm still missing the feature. And even if I consider an octet, so I have 8 drifters per single dilation rate estimate, I am still missing this feature. But then again, you have to remember that this is the absolute worst case scenario here, at least in this domain. So if I average all of these errors throughout the entire domain, I can get one single number to quantify these fields. If I look at how the error varies as a function of the deployment radius r, we see that for large r, we have very large errors. And this is potentially linked to these filamentation-like features. And for a small r, even if there are errors due to discretization, the triangles are probably going to be more representative of the finite size fluid patch. Another way to look at these curves is that when we go from n equals 3, from a drifter triad to a drifter tetrad, there is a significant improvement in error, but only marginal improvement beyond, which means that considering drifter tetrads would probably be a good balance between the available drifter resources and accuracy during a field experiment. And the key point to note is that here we can understand from the curves that the boundary discretization essentially sets an upper bound on the permitted R values during field experiments based on the error magnitudes. Now, it would have been great if I could just stop here and move on when the error magnitudes are still below 4%. But however, we still need to consider uncertainty from GPS units. And the moment I consider them, the error magnitudes shoot up. And now we see the opposite trend, wherein the error decreases as a function of time. This is because if I start with a large two-hit patch, you're probably going to end up with a fairly large triad at the end as well. And even if we have imprecise measurements of the final positions, those are probably not going to affect the area of the triads too much. Yes.
So I'm a little bit confused about why you're focusing on the average error when you really care about whether or not it's capturing subduction zones, right? And so
Yes.
wouldn't you want to focus on how good is it doing near the subduction zones? And
That is exactly what I'm going to be talking about. That's a great point, though. But yes, so as I was saying, larger R, not too much of a problem, but the moment I go to small values of R, sometimes the uncertainty zones can overlap with the actual driftable region itself, and in some extreme cases, like the examples are shown here, you might get double or more than double the area, the actual area. And sometimes these drifter positions can look like they are all aligned even when they're not. This results in very large error.
Aravind,
Yes.
scaled error is scaled with R? Or
Scale with another representative dilation rate value. So you can think of this as some kind of a percent error. Okay. Yeah, so now when I consider drifter-based dilation rate estimates, the total error is going to be a combination of the two factors. Here the GPS uncertainty sets a lower bound on R, and when I look at the combined effect, we see that there exists an optimal deployment radius where the error is minimized. But as Craig mentioned, we're not interested in averaging over the entire domain. We only need the strongest converging regions. And so if we do the averaging at the strongest converging regions, we still retrieve the same optimal radius. The problem, though, is that we have very large error magnitudes, around 30%. So what do we do? Well, if we think about the applications or the motivations behind the study, you might remember that we are interested in locating regions of strong convergence and not necessarily getting accurate measurements itself. So we try to see how well the drifter-based estimates capture the strongest convergent regions using infinitesimal dilation rates. We see that for R equals 50 deployment, only around 57% of the strongest regions are being captured. But the moment we move to a 250-meter deployment, we capture 84% of the strongest regions. Now this is encouraging. And now if I plot this overlap percent as a function of radius, we still retrieve the 250-meter outcome. Now what you need to keep in mind is that I did this analysis in a numerical model using 1.5 million drifter trajectories. And this is not going to be available during experiments. Usually you get like 20 to 30 drifters per experiment, which lasts over a few weeks. And that means you can get a maximum of like 5 to 10 dilation rate estimates. So the question is there a better way to utilize these? Before I actually try to address that, let's look at a case study. And this case study talks about the Lagrangian submesoscale experiment, which is somewhat unusual because they had the ability to deploy around 200 drifters in a single region in a nice grid-like pattern. And this study was done in the Gulf of Mexico, near the mouth of the river Mississippi. So you can expect density fronts to be formed because of the fresh water from Mississippi meeting the salty, dense water in the Gulf itself. And if we take a look at how the drifter trajectories evolve, we see that more than half of these drifters quickly clump together and then get aligned along a filament-like feature. Now you know that density fronts do exist in this region. So is this actually a sign of convergence, or are these drifters just getting trapped in a jet-like feature and just getting pulled along? How do we identify that? Well, sorry, I erased that question here. How do we identify that? We can try to compute dilation rates. So if I use the drifter triad-based dilation rate estimation, we can see that there are some signs of strong convergence along the distribution as indicated by these blue dots. But the vast majority of our estimates are positive, shown in red, which indicates Lagrangian divergence. So the question is, can we convincingly say that this is a signature of a Lagrangianly convergent filament? I don't know. Now, this is where my third study comes into the picture, which was done with Tanay, who's also my committee member, and he's on Zoom today. So in this project, the main idea was to deal with sparsity in observational data when I'm trying to measure these dilation rates. And the main idea here is that I use a machine learning based approach called Gaussian process regression, which can take in drifter trajectories as input and give me velocity fields and also associated uncertainties as output. These reconstructed velocity fields are then used to compute synthetic trajectories, and with those I can estimate direction. That's the idea. Now, why did I go with this method? Well, it's very similar to some techniques that are already popular amongst oceanographers, called like the optimal interpolation, which has been used for decades now. But the key advantage with this method is that we don't have to manually specify some parameters like the correlation length and time scales, or even the signal to noise ratio and so on, because the method tries to optimize these parameters based on observation itself. Of course, the method comes with a share of disadvantages, but these are also applicable to many of the other mapping methods that are out there right now. Okay, so let's take a quick look at how the method works. So the problem statement here for me is, how do I obtain estimates of velocity at some target points given velocity measurements at some data points? The key assumption I make here is that given no prior information, I can assume the velocity at each point to be a Gaussian process, which essentially means at each of these target points, I can assume that given no other information, the velocities can follow a zero mean Gaussian distribution. This also applies to the data points, but then we have measurements at these points in data. What this allows me to do is then solve an optimization problem using purely the velocity measurements to optimize for these hyperparameters in the problem, which are essentially the correlation length and time scales, as well as the signal to noise ratio, and also an amplitude term. And once I know the optimal parameters, I can do some matrix algebra and get a posterior distribution for target velocities given the data and the observational data. Now, statistics tell us that if we have a posterior distribution like this, the best estimate for velocity from this distribution, from a minimum mean squared sense, is the mean of the distribution itself. Okay, so now let's just walk through what the method tries to do. Given no prior information, we can assume that the velocities at these target points follow a zero mean Gaussian distribution. And the moment we have one velocity measurement, we see that the distributions are adjusted because of the posterior. There's more adjustment near the measurement itself and very little effect further away. And the moment we add more and more and more data, you see that these distributions get tighter and tighter. As I was mentioning, the advantage with this method is that not only do you get an estimate, you also get an estimate of the uncertainty associated with this. Okay, so I just wanted to know how this method works by analyzing an analytical system first. The system I chose is prescribed by a nice stream function, which involves a superposition of three waves. This definition using a stream function means that the velocity fields I obtain from this will be non-divergent. So the dilation rates and divergence should be zero. The velocity field I compute analytically from the stream function is what I've shown here. The arrows represent UV velocity, how it looks, and the color in the background is essentially the U velocity magnitude. What I find interesting about the system though is that if I see the entire domain with particles that are colored based on their initial X location, and then I advect them using the analytic velocities, we see an interesting pattern emerge. We have this nice coherent central jet that is meandering about a system of coherent vortices, rotating vortices. So for my analysis, I consider two dynamically distinct regions in the domain, one being the central jet and the other a gyre core. I released a cluster of 36 drifters within each of these dynamically distinct regions, and vectored them, extracted the trajectories and fed them as input to two different GPR computations. And then if I look at the reconstructed velocities at the initial time instant for the central jet as well as the gyre core, and I compare it to the analytic velocity, the first thing you probably notice is that the fields look very, very different. However, if you look at where the drifters are at that instant, and if you look at a small region around it, we see that there are some similarities. Now, if we leverage the advantage of the method I mentioned earlier, which is that it gives us uncertainties associated with the estimates as well, and I look at the uncertainty field, and I just say that I'm okay with an error of 4 centimeters per second, I can define these regions of confidence in the region. And if I look inside these regions of confidence, I see very low error in both of these reconstructions. If I look at how this evolves as a function of time, we see that the contour, the region of confidence, moves along with the drifter cluster while always having low error magnitudes inside. Now that we have understood how this velocity reconstruction works, the next step for me was to look at how trajectories compare. So essentially, I computed trajectories using the GPR reconstructed velocity fields. Those are synthetic trajectories, and I compared them to the true trajectories computed using the actual analytic velocity field. I compute the error in trajectories as the distance between final points of the two types of trajectories. And if I plot the error in trajectory as a function of their initial location of the points, which are seated throughout the domain, I notice that there are large magnitudes of error, especially in the gyre core case, within the Eulerian region of certainty. This means that even if I initialize particles within my confidence interval at the initial time instant, it need not remain exposed to accurate enough velocities for it to produce accurate trajectories. To see what's going on, I seeded particles throughout the domain, tagged the ones that start within the domain with red, and I auto-colored them using the expected error. And if I see what happens, we see that some of these particles quickly leave the instantaneous Eulerian contours. And as a result, they get pulled very far away from the domain. And that is the reason we see the error. This means that the way I've defined the Eulerian uncertainty contour, it is just not applicable to Lagrangian calculations. So what I do is that I compute an average of the variance associated with these velocity estimates along particle trajectories, and this then allows me to define new uncertainty contours, the Lagrangian uncertainty contours. If I look within these regions, the error magnitudes and trajectories are very small. And if I look at dilation rate fields, which are essentially dilation rate errors for this system because the dilation rates are supposed to be uniformly zero everywhere, we see very low dilation rate magnitudes inside these contours. So now I'm fairly confident that I have a method which can be used for Lagrangian calculations given sparse data. Let's see what happens in the laser analysis. Well, this is where we stopped the last time. We had some dilation rate estimates which were sparse and which couldn't really tell us what was going on very well. If I look at the GPR-based dilation rates, we see a clear signature of a blue convergent film that lies very close to the drifters. The key observation is that this filament lies within our Lagrangian uncertainty contour, so we can be pretty confident about this filament's existence. And that is what will bring me to my conclusions for the day, which is accumulation regions of these buoyant particles in the ocean are revealed by signatures of dilation rate and not the instantaneous Eulerian divergence. Strong signatures of Lagrangian convergence on the ocean surface, as revealed by dilation rate, also locate strong vertical displacement of material. We can estimate these dilation rates in the ocean using the triads or tetrads, and while they are error prone, the estimates themselves, these estimates can be used to locate regions of strong convergence. And finally, if the available drifter data is sparse, we can use a GPR based reconstruction to obtain fairly reliable dilation rate fields. Looking into the future, I leverage this GPR method and say, okay, can I use this GPR based reconstruction out in the ocean to potentially get an observational verification for the fact that dilation rates can locate where subduction occurs or vertical displacement occurs? That's the first thing. And the other idea that really interests me is the potential of doing a full 3D reconstruction using GPR, using drifters that have strokes of various lengths, essentially allowing drifters to track currents at various depths. Another thing that's interesting to me is to use the GPR method. So I've demonstrated that the GPR method is not only useful for dilation rate calculations, it can do other kinds of Lagrangian calculations as well. And there's plenty of literature out there talking about the value of a Lagrangian coherent structure analysis using metrics like FTLE and so on. So given the power of this GPR-based Lagrangian analysis, natural next step that I would like to take is potentially use the sparse data available in the ocean to do these coherent structure-based calculations. And finally, combining this as well as the 3D modeling idea combined, can I use 3D reconstructions using GPR to look for reduced order visualizations of fluid flows in the ocean and maybe even obtain the structure, the transport pathways that exist in the bulk of the ocean? And before I conclude, I'd like to just take a few minutes if you don't mind. So I've been here for 5 years now, as Michael mentioned. And it has really been amazing working with you, Michael. I honestly believe that I would not have made any of this progress without your constant support. I've developed in many ways, and not just scientific. Research-wise, even I've learned a lot about general life as well. Even with science, one of the things I learned a lot was not just how to do research, but how to communicate it. I was a very lousy science communicator before, and Michael was really kind and accommodating throughout the 5 years, especially during COVID times. So really, I'm really grateful for that, Michael. Thank you. And then the committee, I am really glad that I was able to have conversations with you about all of the science. I don't think I've had the opportunity to know you, all of you throughout the 5 years, but ever since we have started talking about the science, I've appreciated all of your input. So Safa, I remember, always had a very practical approach towards these problems, and especially when it came to methodologies and method implementation, and that was really helpful. Right? Yeah, I think I've known you only since I formed this committee, but before, when I started PhD, I noticed that you were the one in the seminars asking all of these fundamental questions. And you've done that with me as well, and that has actually helped me understand things from a different perspective as well. Jessica, I know that we have not been working on anything at all. We have actually been working on CFD analysis of the flow inside human lungs. So we have been working on this for like a year now, and only now have all the pieces finally started coming together. So thanks a lot for extending the opportunity to do that. Tamay is on Zoom. I think the first time I met Tamay was on boat in the Mediterranean Sea as part of the Calypso experiment, which is spearheaded by Amala and Eric Pissarro, amongst many others. And I really had a fun time working on this last project with you, Tamay. like it was like whenever I had results to discuss with you, you're always encouraging and really happy to help, and that really made me happy as well. One thing I would remember though is the ping pong games we had on the board. Those were fun. Of course, there are plenty of other people I'd like to thank as well. One thing that I felt I was very lucky to be part of was to get the opportunity to work with the Calypso group itself, which honestly has the who's who of oceanography today, and every one of those Calypso meetings I've attended were really eye-opening, and I've learned quite a lot from those meetings. One special person I'd like to thank is Sutanu. I don't know if he's on Zoom today. I really had a great time working with him on the vertical transport project, but now he has also extended an opportunity for me to work with him after my PhD. So thanks a lot, Sutanu. And of course, this PhD would not have been what it was unless I had a few friends that I made here in Boston. All of you guys who are here, and I'm guessing probably Guy has joined from Italy. I see Ali's name here. So I don't want to take up names, but everyone, thank you for being with me. And finally, I would also like to thank my parents who have had my back since day one. And also Krishna, who's in the audience now, for the last 7 years. I really don't know what I would have done without you, so thank you. That's it from me. Thanks.
Okay, we'll open it up to questions. I'll monitor the Zoom chat for any questions that are brought up there, but we'll open up to questions in the room first.
Yes, sir.
So I wanted to ask you about the GPR-based method when you took found this contraction region of the optic valley.
Yes.
And can you say something about the red region that controls? So is that
So the red region indicates Lagrangian divergence. It is potentially a consequence of conservation of mass, because when there is strong convergence, you expect material to move away from the neighboring regions and move towards the contracting region. So this is a signature that you generally see in dilation rate maps. But then again, what goes on beyond this contour of certainty is not something we can trust as well. But what I've noticed is that this signature of the convergent filament matches pretty well with what I saw in the SST field I obtained from NOAA. So I feel like this is a reasonably good interpretation of what's going on.
were there no drifters in the red region within the contour that you could verify that?
Okay, so that's a great question. I don't know if sorry, screen sharing is gone. I'm going to turn it up again. I don't know if I have a slide on this, but there's a good chance. Unfortunately, I don't. Check back on for this wrong. Yeah, so you brought up a great point. There were a number of other drifters in this region as well, and they essentially improve my dilation rate estimates and reveal more convergent signatures. The reason why I just chose this set of 28 drifters was that it falls within the 20 to 30 range of drifters that I can usually expect. And it is also the set of drifters that converges from a nice cluster that is fairly well spaced apart to forming this filament over the course of just a day. Technically, I had access to like 187 drifters, and I have results that show how it really improves not only the dilation rate field, but also the region of certainty. And we can talk about that afterwards as well. And then it really matches what the SST fields, SST fields receive. Sure. Thank you. There we go.
I was kind of curious about the deployment of the drifters and how that happens, and how do you make sure you don't disturb the waterways when you are deploying them?
Okay, that's a great question. So the drifters are not too big. The buoyant parts are usually too big. What you usually do is you deploy them over length scales of about 3 meters, which is like the width of a boat during an experiment. Well, you can make an argument that when you deploy it, it's gonna disturb the flow a little bit, but I think the degree of disturbance is not significant compared to the underlying flow velocities. And over the course of a few minutes or hours, that would just be dissipated. Thank you.
Any questions from the virtual side?
Silent?
John, silent.
Yes, not a great job of explaining everything.
I don't know. You're fine. So I'll go ahead and ask a question, which is always unfair because I either ask a question or the answer to, or ask a question I know you don't know the answer to. So you've done a lot of this analysis of trajectory information, which is sort of focusing primarily on just what's happening from a purely U and V perspective. Can you comment a little bit about sort of what's going on from a sort of process perspective? Particularly, can you talk a little bit about what you're expecting from sort of an oceanographic perspective of what's going on here and how your results are unveiling this?
Okay. So the first thing I would say about that is this is just a kinematic description of what is going on. So it doesn't really tell us the underlying mechanisms because I'm really looking at UV related information. But to actually understand the process going on in that region, you'll have to look at the dynamics, which involves looking at density, which is formed comprised of temperature and salinity and so on. So this kinematic analysis is going to give you an idea of some dynamics. The flow features and how it looks in the region, but it really does not tell you underlying mechanisms. Is that what you're looking for?
Be a practical. What would it take to apply this GPR to the, we're on the boat in Calypso? Now that you have it working.
Yes. So, well, I was on the boat. I had not really understood this method well enough to apply it properly, but now I have a decent working knowledge. I managed to parallelize the code that I initially had, and I noticed that the memory as well as computational time scales as n squared. But then with respect to computational time, when you start parallelizing it, of course, the CPU time still goes as n squared, but you can really reduce the wall clock time. The 28 drifter analysis, I think it'll be done in around something of the order of a few minutes. But the 187 drifter analysis, it's gonna take a long time. Computational costs are very high. Memory requirements are also very high, of the order of hundreds of gigabytes. But this particular computation is relatively pretty cheap. But then again, there are also packages that are accelerated using GPUs now these days. I've not done the GPU acceleration, and those can really help with cutting the computational time costs. So, when on a boat, if you have access to a machine on the land, I think it's usable.
Can you comment a little bit on settings or properties of the deployment strategy where you would expect maybe it wouldn't work?
Okay, so the key thing here when I'm looking at GPR based estimation is that I need to have a decent number of drifters that sample the same dynamical feature. what is a decent number? That is something that is yet to be determined. I did some analysis on the analytics system, and I noticed that the fields degrade considerably when I start sampling the region using maybe 10 drifters instead of 36 drifters. I see a significant degradation in the field. The problem is that when we look at observational data sets and we have drifters that are isolated in a different dynamical system, then you're gonna see some really weird results from this method. But as long as you have a sufficient number of drifters sampling the same dynamical feature, I think you should be fine. So, yeah.
For this GPR, for this second, you are only using this second measurement, or you are using the history data, history estimation plus this second data?
That's a great one. So here for this particular analysis, I considered drifter trajectories that were sampled every 30 minutes over 3 days. So I have a really nice model built up from the history, and then I use it to do these synthetic trajectory computations for a 1-day time interval, which is what I did here. And that's an interesting point as well. I also noticed that whenever I pad the data on the left and right side, the earlier and later times, if I have data and drifter data for earlier and later times than the time interval of interest, where I'm computing these Lagrangian metrics, I see a significant improvement in these confidence intervals, the sizes of the confidence intervals as well as the results. Again, it's like a drastic improvement the moment you start adding data, but then it's like decreasing benefits as you add more data.
Another clarification question. So you're showing up the dilation rate, but you have the a time evolving flow field.
Yes.
No. Always within the region of the contour, or the time evolving flow field is complete, or it's like patchy, or?
So the way I've done things here, I have directly used the analytic model that I obtained from the GPR for U and V. So I can avoid patchy results. I can get a very, the resolution can be as high as I want. Yeah, since you mentioned time evolving, I can also do a time evolving dilation rate computation and look at how these features evolve as a function of time. And I've done that as well, and they're actually pretty good. I can show you images after this.
Any final questions from the audience, and then we'll move to the committee questions. Okay. Thank you all so much. Thank you, Aravind. Very nice job.
As soon as I tell them,
What ends up happening
they get
when you
nervous, right? It's
end
like.
up doing